curve is defined by the equation y equals x cubed. Can you estimate the slope of the curve at point 2, 8? Okay, well this is a little bit more tricky. We've got ourselves a curve, and y equals x cubed is a bit nasty. And we know that when x equals 0, y equals 0, because 0 times 0 times 0 is 0. So we know that the graph is going to go through the origin. Negative 1 cubed is negative 1 times negative 1, which is positive 1, and positive 1 times negative 1 is negative 1. So negative 1 on the x-axis is going to have negative 1 on the y-axis. So we're going to have a point here. And then 1 times 1 times 1 is 1. So we've got the mirror image here is 1, 1. And then negative 2 times negative 2 is positive 4, and then positive 4 times negative 2 is negative 8. So negative 2 cubed is negative 8. So if this is negative 2, we're going to have to pretend that negative 8 is down here somewhere, and it's going to be way off. Actually, that doesn't even look like it's a proper curve. If we're going to shorten the y-axis, we need to shorten the x-axis. Seriously. So negative 2 is going to be really close to the negative 1. And the negative 8 is going to be a long way off. This is going to look very strange. Okay. That's probably a bit better. And then 2 times 2 times 2 is 8. So if we put our 2 right here, and then we put our 8 right at the top, then we'll have something a bit like this. And then our curve will have a very steep slope, gradually getting smaller as it snakes down and comes down like this. So this is what our curve is probably going to look a little bit like, but that's not a very neat curve. So I want to introduce you to the Desmos graphing calculator, and then we can click on graphing calculator, and now we type in our y equals x, and we use this caret symbol to get the cursor up, and then that's y equals, no, not y equals x to the 6. On my computer the caret symbol is over the 6, but we want y equals x cubed. So this is what our y equals x cubed looks like. Now we want to know what the slope of the curve is at y equals, sorry, not y equals, at point 2, 8. So let's plot that point, and that's going to be all the way up here. Okay, so that's quite a steep slope. So the first thing we notice is that the slope is constantly changing, so we can't get the slope of the curve at all. Although I suppose if we pick 2 points that are really far apart, and we draw a straight line between those two, we could get the average slope of the curve across all of that, but that's not really helpful because we want to know what the slope of the curve is at point 2, 8. So really we want to be picking points that are close to point 2, 8. Alright, let's try 1, 1 and 3, 27, which will be either side of 2, 8, and then we'll try and get the slope of that curve at those points. So let's just put these points down. 1, 1 and 3, 27. Oh boy. So we want to get a straight line through these points and find out the slope of that curve. Let's go ahead and do that. Okay, so we're looking for the equation of a straight line through points 1, 1 and 3, 27. Well, we know how to do this. This is just delta y by delta x, which is equal to 27 minus 1 over 3 minus 1, which is equal to 26 over 2, which is equal to 13. So we're estimating the slope here as 13. Let's plug that into our Desmos graphing calculator. So let's try y equals 13x. Okay, so that's the black line, and it's nowhere near the line, so we're going to have to shift it across. So let's say minus 10. It's getting closer. Minus 12, minus 13 rather. I miskeyed that, I was going to type 12. Minus 15, minus 16, minus 17. Yay, we're touching the point 2,8. Okay, well, it's not exact, but it's close. Could even move it across a little bit more. And that's actually pretty beautiful. Okay. What if we hadn't got 13x? What if we'd got, say, 10x? And we make that minus 14, 12. Look at that. See, that's also pretty close. And what about 60? We said 13, didn't we? What about 15x? And we subtract a bit more from it to move it across. Well, this is just pure guesswork here. That's also pretty close. So we can't be exactly sure what the slope is, but it's probably around about 13. Maybe could be anywhere between, say, 10 and 15 is probably close. I mean, it's not going to be as high as 25, is it? Yeah, that's way off. Okay, so 25 is way off. So we're probably looking at somewhere between 10 and 15. Probably something close to 13, maybe, as an estimate. Can we get a better estimate if we make those 2 points closer together? Let's try getting them closer to 2. Let's say 1.5 and 2.5. Oops. Okay, so 1.5 cubed is 1.5 times 1.5 times 1.5. Well, let's say 1.5 is 3 over 2. And if I cube that, that's equal to 9 over 4. No, 9 over 8, sorry. 2 cubed is 8. And so that's 9 over 8. The graphing calculator can turn that into a decimal, I don't need to. And then 2.5 is 5 over 2. And 5 cubed is 5 times 5 is 25. 25 times 5 is 125. And 2 cubed is 8, so that's 125 over 8. So let's plot these points. 2.5 comma 125 over 8. Alright, let's zoom out until we find these 2 points. Okay, so they're a bit closer, and now we need to try and, well, I've done something wrong, because 1.5 comma 1.125 is not on the line. One 1.5 is 3 over 2. 3 cubed is 27. That should be 27 over 8. There we go, that's on the line. Okay, so now we want to join these two lines up, or these 2 points. Okay, so that's not 9 over 8, that's 27 over 8. Why did I square the 3 instead of cubing it? Okay, so we've got 3 over 2 comma 27 over 8, and we've got 5 over 2 comma 125 over 8. So again, we've got delta y by delta x, which is equal to 125 over 8 minus 27 over 8, and all that is divided by 5 over 2 minus 3 over 2. Hope you like fractions. Okay, so this is basically 125 minus 27. 125 minus 20 is 105. 105 minus 5 is 100, and then we need to subtract another 2, so that's 98 divided by 8, and all that is divided by 5 over 2 minus 3 over 2 is 2 over 2. Well, that works out nice, so that's divided by 1, so that simplifies to 98 over 8. Okay, so let's try the line with the slope y equals 98 over 8. X, and now I need to line these up, so let's subtract, say 10, no, 12, 13, 14, 15. Okay, that's close. Not that close. Let's make that 16. There we go. Okay, that's very close. Okay, so 98 over 8. What is 98 over 8? That's 98 divided by 8. That's 12.25. So we've got an estimate of a slope of 12 and 1/4. Well, that's not bad. If we bring it closer, we might be able to get an even better estimate. In fact, let's do that. But this is going to take a little bit more thought. Let's try. So we want the slope at 2,8. So let's say 2.1 and 1.9. That's within 1/10. So let's try that. So 2.1 cubed. So that's 2.1 times 2.1 times 2.1 is 9.261. 9.261. So that's my 1 point. And my other point is 1.9. Let me just make that 6 look more like a 6. And then 1.9 times 1.9 times, oh, that's not what I wanted to type in, 1.9 times 1.9 times 1.9, 6.859. 6.859. And again, delta y by delta x. So that's 9.261 minus 6.859, all divided by 2.1 minus 1.9. Okay, let's put that into the calculator. 9.261 minus 6.859 equals 2.402. 2.402. And we're dividing this by 2.1 minus 0.9. Well, that's just going to be 0.2, isn't it? But divided by, open brackets, 2.1 minus 1.9, which is indeed 0.2, and that comes to 12.01. 12.01. And let's plug that back into Desmos. And let's do y equals 12x. And let's even put the points in. So we've got a point 2.1 comma and 2.1 cubed. There we go. And the other one was 1.9 and 1.9 cubed, which is 1.9 times 1.9 times 1.9, 6.859. Pleased to hear they both lie on the same curve, and 2.8 is right in the middle of the two, and that line does indeed look very, very close indeed. So the closer these 2 points get, it looks to me like the closer our slope is to 12. So just by guessing and refining our guess, by making the points on the slope ever closer together, we're estimating that the slope at that point is 12. So the answer I'm giving is 12. And that's my estimation. Okay, so that's how we can estimate the slope of a curve when the slope is constantly changing at a given point. We can create 2 points either side of the point that we're interested in and bring those points closer and closer together, and we can look to see what the slope of the curve is. So it's not a calculation, it's an estimate. We're basically guessing, and we're guessing that the slope is 12 for this one, but it's not a blind guess, it's an educated guess. Okay, can we do better than that though? Because that was a lot of work, and what would be really nice is if we had some kind of a function where we could plug in our point and it would give us the slope. So what we would like is something like an f of x is equal to let's say x cubed. It could be anything. And then we want another function, say g of x, such that if we plug the x in, it will give us some equation that will spew out the slope at that given point. That would be convenient. It would be a heck of a lot more convenient than what we've been doing. We've been taking some curve and we've been looking at 2 points on the curve and getting the slope of the line that passes through those 2 points, and using that to estimate the slope of the curve, and that's called a secant line. If we can get a curve where the line touches the curve in exactly one place and the slope of the curve is exactly parallel at that particular point, that would be the slope of the curve, and that's called a tangent line because it touches in exactly one place. But to get a tangent line would be very, very difficult. In any case, I think that's enough for this lesson. And I'd like to leave you with a question, and I'll pick up in the next lesson where we'll be looking for just such a function that can spew out the gradient of a curve at any particular point.